Now we're going to begin our long journey on series. Remember what I have been saying to you. Series is not difficult. It's just different. When we talk about series, we're going to talk about series in terms of n, and we'll see later on that x will show back up, and we'll see what this has to do with Taylor polynomials and so forth. So what we're going to do is we're going to take our knowledge of infinite sequences and we're going to build on that to talk about what happens to our infinite series and what convergence and divergence looks like for series. So remember from our last lesson, for an infinite sequence, when we're talking about convergence or divergence, we're exploring what the terms are doing. Just the terms for large values of n. If the later terms in that infinite sequence get very near a value and stay there, then that's sequence convergence. So that's what we were looking for. With a series, we're taking those terms that we generated in our sequences and we're adding those together. So a series does not equal a sequence. Sequence convergence doesn't have a direct bearing on series convergence. The outputs of our infinite series are really different from those of our infinite sequences. Now what we're concerned about is, do our sums approach a particular value and stay there? That's what series convergence looks like. If those sums are bouncing around like the terms in the sequences did, then that is divergence. Or if they're growing without bound, that is divergence. But still, for our series, in the absence of convergence, we have divergence. That is the same as it was for sequences. So we're going to run some tests on our series. We're going to try to determine whether those sums are converging or not. The problem with series, or the difference with series as opposed to sequences, is not one test is a fit for all series. If so, we wouldn't have to learn so many different convergence tests. What we're going to spend the next several lessons on are different techniques, different tests that we can use to determine whether our sums are approaching a value or not. And there turns out to be quite a few of those tests that we have to learn, and then we have to decide when and how to use those. So let's start talking about series. Let's see what a series looks like. Remember, if we have a sequence, remember our sequence is made up of elements or terms. And they're generated starting with n equal 1, unless we're told different. And a sequence is nothing but just a set of numbers. If it's infinite, it has the comma dot 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 at the end. If we take all of those elements and we add them together, and that's what this Greek symbol means. This says we are going to take the sum of all the elements or terms in this sequence, and we're going to add them together. That's why it looks like a sub 1 plus a sub 2 plus a sub 3 plus dot dot dot. If we have an infinite sequence and we add all those terms up, it leads us to an infinite series. Now, we can, or we don't have to, identify an infinite series by placing the n equals 1 on bottom and the infinity symbol on top. In the absence of that, we are to assume that it is an infinite series. That's just information on notation. So let's say we're given the infinite sequence a sub n equals, and this is equivalently written as 1/2 to the n, but 1 to the n is 1. So we're going to generate the terms in this sequence. If we want to find the series for that sequence, we're going to add all of those terms up. And never more than in this context is it important that you remember the plus dot dot dot. That has to be there. Our series that we are working with are infinite series. It turns out that the nth term for the sequence and the nth term for the series are the same, because series are sums of sequences. So that's what they have to do with one another. Now, let's talk about properties of infinite series if we wanted to add series or multiply things by a series. There's one property here that says if a sub k and b sub k both converge, and c is some constant value, some real number value, then if I multiply a sub k, and it could be true for b sub k as well, by a constant, then that doesn't really affect convergence or divergence. If this is a real number value, and it will be if that series converges, and we were told it does, then when I multiply that real number value by another real number value c, it's still going to yield me a real number value, which means that my series converges, because that's what our sums are going to be now. We're not worried about what the terms are doing as n gets large. We're worried about what the sums are doing as we add more and more and more terms. This says that if I take the sum of two convergent series, the sum's going to converge as well, because a real number plus another real number yields me a real number. All right? So that's all these things are saying is, for a convergent series, multiplying it by any real number, positive, negative, anything like that, doesn't change convergence. Taking two convergent series and adding them together still yields me a convergent series. So sometimes if I'm given a series and its nth term has different pieces, I can see what each separate piece is doing. And if each separate piece of the series is converging, then the sum of those pieces must converge as well. And we'll see that when we work some examples. So if the series diverges and c is any real number value besides 0, then multiplying the divergent series by any real number won't change divergence. The only way that it might change it is if c were to equal 0. So this says multiplying an infinite series by a constant other than 0 has no effect on convergence or divergence. If a sub k converges, then c times a sub k converges. If a sub k diverges, then c, as long as it's not 0, times a sub k must also diverge. Most of the time what you're going to see as far as notation is concerned, we'll just take a little notation aside here, 99% of the time you're going to see n. All right? But just as is written here, I can use any lowercase letter. We will see that mathematically it's accepted that that lowercase letter is usually something from the middle of the alphabet. I've seen kind of all of those used in the context of sequences and series. So don't get attached to n. It can be any letter, usually a letter from the middle of the alphabet, but it doesn't have to be n. For us, most of the time, it will be n. If you're asked to find whether a series converges and that series is given to you in terms of k instead of n, then you run the limit as k approaches infinity. Just watch your notation. All right, the grouping of terms when it comes to a series sum. The terms of a convergent series. Now, this is saying we know up front the series converges, not true for a divergent. The terms of a convergent series can be grouped in any way, provided that the order of the terms is maintained. In other words, if I have a series that is something that looks like this, then I can group these two together, or I could group those two together, and it's not going to mess with convergence. That's what it means, provided the order of the terms is maintained. I can't mix the terms up, but I can group them in any way, and the new series will also converge with the exact same sum as the original one. So the sum of the first n terms is a finite series. We'll call it a partial sum. The actual sum of an infinite series is an infinite sum. It is the sum. But if I have a finite number of terms, and that's what that symbol tells me right there. Here I'm starting with k equal 5, and here is a sub k. This is what's happening to k, starting at where they tell me to, and stopping where they tell me to. I start at k equal 5, which means the first term that's going to be in my sum is 3 times k, where k equals 5. I'm going to add to that the next term, which was 3 times 6, then 3 times 7, 8, 9, and 10. You get the idea. This is a finite series, not an infinite series. There are a finite number of terms. An infinite series is going to be denoted by having the infinity symbol on top. Here's one, a sub j, where a sub j is 1/2 to the j. I take that sequence, I generate the terms, I start where they tell me to. Here they told me to start at 0, not at 1. I generate those terms, and this symbol tells me that I'm dealing with a sum, to put the sum in there. All right? This should actually be 3. Not real sure why that wound up 4. But you get the idea. Our series are sums. And so when we talk about our first sum, and then our second sum, and then our third sum, those sums are very different than our elements or terms of our sequence. So here is one example. This is not the only way series converge, but it's one example of series convergence. Let's say we started with 1 square unit by 1 square unit, and we divided it in half. And then we divided that half in half, and that half in half again, and then the other half in half, and then the other half in half. And let's say that we added all of those up. Let's say we wanted to find the area of our square. Well, that would be 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. And we would continue to add smaller and smaller and smaller fractions. Everything that's here, those fractions get super, super small. Why? Because their denominators get super, super huge. And it turns out that even though there are an infinite number of terms in this sequence, and therefore an infinite number of terms added together in the series, that it's still a value of 1. The partial sums here, the first sum is 1/2. The second sum is 1/2 plus 1/4. The third partial sum is 1/2 plus 1/4 plus 1/8. That's what our partial sums would look like. And so we would find our nth partial sum, and that looks like S sub n, not the same as A sub n. Sometimes it's not just a matter of our sequence elements or terms getting smaller and smaller and smaller, and then when we add those up, we can count on, because A sub n, is tending toward a really small value, we can't always say that that means series convergence. Sometimes, even though we're adding smaller and smaller values, we're still adding enough of those as we tend toward infinity that even though they're getting smaller and smaller and smaller, the sum still diverges. So I just wanted to make that point before we move on.